Welcome back. We are almost there for training our first machine learning model, but we have still one problem to tackle. That's representing a molecule. As we discussed before, we have an input of molecule and we want to convert it into some numbers, and we'll see how we can do it. As we have seen in our Google Colab notebooks and looking at the QM9 dataset, we have input of smiles, which is a string. But a machine learning model would need A's and B's, which are numbers on which we have weights W1 and W2. So the challenge is converting these smiles or molecular representations into numbers, or some ways to input into a model. One way is to describe this molecule in terms of its descriptors. For instance, if we have a molecule benzene, we can say the molecular weight of benzene is this, exact molecular weight is that, number of hemi atoms is this, and number of H bond acceptors is that. So we can have a list of all these properties, and those would be our A, B, C, and so on. And this could be the input for a machine learning model. This set of descriptors is from RDKit. You can get a complete list of these descriptors from going to this website, and those descriptors can then be selected and put into a machine learning model to do the prediction. Another way of representing a molecule is called fingerprinting. And in a fingerprint, what is done is you consider an atom and look at the surrounding atoms, and you have a vector which is consisting of ones and zeros, and those ones come from positions where you see something. For instance, let's say you have at the 0th position NH, and in this vector the first position is reserved for NH, and you see NH over there, and you put in a 1. If you don't see something, it'll be a 0. And this position is assigned to something, and we don't have that thing in this molecule, so this is a 0. And the radius of this decides how many atoms further you are looking into. So at this is a radius of 1, and radius of 2, a radius of 3, and based on that you have a space allocated in this vector, which can either be 1 or 0 based on what the functional group is and whether it's present in the molecule or not. These are some of the fingerprints available in the RDKit package. We'll be mostly using Morgan or circular fingerprints for these, and this would give us the vectors of 1s and 0s, which would be A, B, C, D, E, and so on. And while training, the weights could be determined by the machine learning model. Another way of representing a molecule is converting into a graph. A molecule, as you can see, has atoms and bonds which can correspond to a node and an edge in a graph. And these nodes and edges can then have features like what is the atomic number of this atom over here, what is the hybridization, what is the charge, whether this bond is a single bond or an aromatic bond. You can embed those features and then use those features in something called graph neural networks, which we'll be doing later in this course. And this is one way of featurizing a molecule. In the last lesson, you saw how to convert a smiles into a feature or molecular representation. And in this lesson, we'll see how to do that implementation in Python. There are several featureizers of molecular representations available in packages like DeepChem. But here we'll look at some of those which we discussed in the previous lesson, which is the descriptors and molecular fingerprints. Unlike dataset splitters, we don't need to convert the entire dataset into a DeepChem dataset for this. They are just functions that we can apply on some smiles representation. And let's see how we can do that. At first, we need to install DeepChem and RDKit. and let's install them. And as before, we'll do all of this on the QM9 dataset with the HOMO-LUMO gap as a target. And we'll featureize it. We'll apply the featureizer to the entire dataset and then show how we can split it randomly. Let's wait for the installation to complete, and it's installing SciPy, it's installed RDKit and DeepChem2. So it's ready. We can download the dataset, which is the QM9 dataset. It has loaded. Instead of using the entire dataset, we'll just use a fraction of it, again in this case, which is 10%. And we'll use smiles and gap as before as our dataset and discard all the other columns in the dataset. So we'll use Morgan Fingerprints as an example of a featureizer, and other featureizers are available here. We can click the link and see other featureizers or molecular representations that we can use for training a machine learning model. But this implementation is for the Morgan Fingerprints. So first we'll load the libraries needed, which is DeepChem and RDKit, the chem code from RDKit. What we are doing here is we are going to use radius is equal to 2, and if you remember from the lesson before, the radius is number of bonds you pass through to get to an atom, and we set that as 2, so we are just looking at 2 bonds. And size is the length of the vector of zeros and ones. We can use 100 over here for the size as vector. And for featureizer, this is the simple code. First we create the object with featureizer, which is dc.feed has the circular featureizer. We say size of 100 and radius of 2. It creates the object that is needed for featureizing it, and we can then apply it to any smiles representation. Let's for example apply it to ethane, which is 2 carbon atoms, and smiles is CC. And if I click on play, we see that it has generated an array of zeros and ones, and it depends on where CC is. You see just 1 over there, 1 over here, and that's all others are 0 in this case. And this will be of length 100, so there will be 100 zeros or ones in this case, and this is the featureizer that we want. And now these arrays or these numbers can be the A's and B's that we needed in that model. Remember, the W1s could be the weight for this one, weight for the other one, weight for the other one, and so on. And this is one way of converting a smiles representation to a numbers or array, and this numbers would correspond to a particular molecule. We can apply the entire featureization to our dataset. A way to do that is using the apply method in pandas data frame. So we say from the dataset, select the smiles column, and on the smiles column apply the featureizer. Apply this function, which is featureize.featureize, and this should work on the entire dataset and give us the features for each of those smiles. And those smiles with the feature part is stored in another column, which is called FP. And once this is generated, we can look at the top of those entries, and we see now our dataset has smiles column, the gap, the HOMO-LUMO gap, and the FP part, which is the fingerprint, which contains zeros and ones. So essentially this FP could be the X for our molecular input, a molecular representation to our model. So this could be the X, and the gap could be the Y. And so now we have all numbers in there, which would help us to train a machine learning model. This is just the molecule fingerprint, but we could also look at descriptors. which include like molecular weight, number of valence electrons, maximum and minimum partial charge, and number of rings and other things. A detailed list of those descriptors can be found on RDKit website, but the descriptor that is implemented in DeepChem uses 208 descriptors, and you can look at the documentation on DeepChem and see what those descriptors are. But we can create the featureizer as shown over here. We have dc deepchem.feat, and from there we create the RDKit descriptor, and there are a lot of functions in here which you can use. So there's use fragment and is normalized, so there's a description of all of it in this, but we can just use the featureizer as is and then see how it does. And we can apply the featureizer as before to ethane, and we'll see a list of numbers now. And these numbers are pretty much, we can consider them to be unique for ethane molecule, and this is one way of converting your string representation to a array of numbers, a vector of numbers, which can then serve as an input to our model.